In this lab, we will do a little bit of analog signal conditioning, improvement of its output. So let's open our main code in our project 2021 ing and in analog.c. So in this code, I will flash it once more in the development kit to see how it works. And let's look at its output. So basically what we see here is that light level is a little bit changing. 3, 8, 4, 3, 4, 7, 4, 6. So it's relatively stable, but it's possible that we could have had a noisier signal that we would want to filter out. So first thing that we need to do is check out the schematics and see if there is some analog filter on this board. So let's go to launcher. Let's go to schematic and layout files for our development kit. And this starter kit schematic. And now we need to find the light sensor. And the light sensor is right here. And it's very simple. It's a photo transistor. You can find its part number right here. Let's just check out. It's possible to find it. Also here you can find its characteristic information. So for example, current versus illuminance, you can see, for example, if it lets through 1 milliamp of current, it means that the light is approximately 4 or 3,000 lux. Okay, so it's good. But now let's look at the schematic. And the thing is that usually it's a good practice to put some capacitor between the analog signal pin and ground, or if it's a differential signal between the differential lines and from both differential lines to ground, capacitors which are 10 times smaller than the one that is between the pins. But as we can see here, there's no capacitor, so there's no analog filtering on the board, which is not great because if there is some high frequency noise because of the anti-aliasing or aliasing thing, it can go into our schematic and get us wrong results. So analog filtering on the board is practically always, almost a mandatory thing. So let's see, maybe the capacitor is somewhere else. Let's look for less light sense pin. And it is analog comparator 0 channel 6 or PC6. But yeah, it looks like there's no analog filter on the PCB. So what we can do is normally we have this excitation pin, there's this photo transistor, there's a resistor to ground, and the microcontroller is just connected right there. This microcontroller has a small RC filter built in. You can enable it, and if you disable it, then there's a transistor which basically connects the input directly. So this is a bypass thing. So we want to enable this internal RC filter to improve our analog signal a little bit. To do that, this chip has it built in. So what we can do is we can select in analog to digital converter settings, instead of low pass filter bypass, there's this option to have filter RC turned on. So this is the first thing that we will do. Let's build it and let's see how the output changes. Maybe it changes, maybe it doesn't change. Let's see. So as we can see here, it changes and it shows lower values. So it adds some time constant. So what we should do is we should also increase the acquisition time, because maybe this RC filter didn't have enough time to charge up. So let's increase the acquisition time, for example, to 8. And let's see what the output is going to be. Let's flash it. If the output changes, it means that there was a difference made. And as you can see now, we let the RC filter some more time to charge up, because this is a high impedance signal. It has high internal resistance. So we need some time for the current to flow through this resistor and charge up this capacitor. And only then we can send the signal into ADC. So we need to wait some time. Okay, so to find the optimum time, we just look for the smallest acquisition time that doesn't change the input. So if I change from 8 to 4, let's see if the input stays the same, then we can also use value 4 here. I set it to 4 and the value didn't change. So let's try also 2. Maybe 2 will also leave no impact. Two also didn't leave any impact that we could notice, but acquisition time 1 was too small. Let's try 1 again. Flash to device, program. Okay, and as we can see, 1 is too small. So we could use acquisition time 2, or maybe for some safety margin, let's say it's 4, because maybe when it's dark, it needs even more time to discharge or charge up. Okay, light level at dark is 200. Internal resistance in darkness is even bigger. So now let's look at acquisition time 8 in the darkness. So now it's light, but when I put it in the darkness, it's smaller. So as you can see, by changing the internal resistance of this circuit, also the acquisition time had to be increased during the darkness, because in darkness, this circuit has even greater internal resistance, and even smaller current flows through this resistor and even slower charges it up to the correct value. So we need a bigger acquisition time actually. So now let's try the 16. Maybe we need even greater acquisition time. And let's look at the output. So in the darkness, I put the finger on this light sensor. So now it says light level 23. And if I set the acquisition time from 8, I increase it to 16, it says 20, it says 13. Okay, let's double it again to 32. Oops. And flash it to device. And now it says 8 and 5. Okay, so we have to try even greater value, 64. Let's build it. Flash it to device. And now it says 6. So previously it said 7 or 6. Now it says 6 or 5. Let's double it again. I think 128 is also a valid value. We can control click on this and we can see all of the values. I cannot put, for example, 50. These are only valid values. Let's try 128. I build it. I flash to device, program. And now it says 4, 3, or 4. So this is light level with acquisition time 128. Now I will try back the 64 value. And if they are the same, then I will use the 64 value because, higher acquisition time means longer waiting, more power consumption, and so on. And as you can see, there's no difference between 128 and 64. So there's no reason for me to use a bigger value than 64 because there's no difference. But as I mentioned before, if I try 32, there is a difference. Previously it was 5 or 6, now it's 7. The offset is too big, so we have to use the 64 pulse acquisition time. So now before sampling, it waits 64 times the clock signal of ADC, which is 7 megahertz, and only then it samples the value. So this analog to digital converter, it turns on this RC filter, then it waits 64 times the clock signal, and then samples the value. The good thing is that this signal is pretty good. It's not very changing. It's, something like between, did I flash it? I don't remember. Flash the device, program. Okay, so it was something like, oh, now it's like 5 or 4. So that's dealt with. And now what we need to do is we can do some other filtering as well. So the first step in signal filtering is having some RC filter to filter out some noise, but you have to wait RC time constant time for this capacitor to charge up to the corresponding signal level. Next thing that we can do is use some averaging. We can, for example, or rather say oversampling. So this analog to digital converter has a capability. It is 12-bit ADC, but it can sample, for example, 16 samples into some accumulator, and you get a 16-bit result, which is a sum of very fast 16 samples. So to do that, we need to change this oversampling rate select selector to 16. In that case, why 16 and not other value? If you have 2 to the power of 12, scientific, 2 to the power of 12 is 4096. And then if you multiply it by 16, you get 65536, which is the maximum value that you can get in 16-bit number. So this is why oversampling select 16 is the the optimum value. So 16 times oversampling, which means that analog to digital converter quickly performs 16 conversions to get a little bit better result. So this is like averaging over 16 samples. And this is override selector. And when we start analog get light level, instead of resolution 12 bits, we need to change it to oversampling number of bits. So now this thing will sum up 16 values. So we expect that there will be less noise because some noise will cancel out between samples. So let's build it and flash it into device. And now the result, you might be wondering why the result is so different, but it's a sum of 16 quickly sampled samples. So this thing is 16 times bigger than what we had before. So if we take this number 6, 1, 2, 7, for example, 725, and we divide it by 16, well, we get what we had before, 3,800 and something. Okay, so that's as some sneaky way of averaging, where basically analog to digital converter samples 16 samples, and we get uh, a little bit less variability in our output. And so that's the second level of filtering. So the first one is RC, analog. And the analog filter needs to have a lower cutoff frequency than the sampling speed of analog to digital converter due to anti-aliasing thing. You can read about it on the internet more. The second thing is oversampling, which is it's almost the same as averaging over 16 values, except we're not dividing by 16, we just leave this bigger number. And the third one is removing top and bottom value to remove some spikes. Let's say you have some samples, but during one sampling there was some mistake, which was small spike. Now, if you calculate the average of 16 points in this case, even though this was some glitch, it moves the average up. So, and the same goes if there was some glitch and one sample was way off to the bottom side, it would move the average down. So it is a common practice that, some people, when they make a digital filter, they just remove outliers. So if the average is this, and there's a point that is very high or very low, then it just gets discarded and the average is calculated from the rest of the points. So let's make such filter. And when we sample the light, let's do it in this way. First of all, let's get 10 samples. Then let's remove largest and smallest one. Remove min and max. And then calculate average of the remaining 8 samples. So let's make this filter, and this will remove some accidental spikes due to some analog to digital converter glitch or some other spike, something like that. So let's update this analog get light level with the following code. Let's create a buffer of 10 values. So I will call it value buffer, and then let's write a loop. Also, let's create some counter for I equals 0, I less than 10, I plus plus. we start the sampling, and then value buffer with index I equals to unlock the digital data single get. So first we do 10 samples, and we sample them into this value buffer. And the next thing that we do is we find the minimum and maximum value inside this value buffer. So let's create these variables. So unsigned integer 32-bit, min value and max value. So min value, I initialized a very high number so that if any value is smaller than that, it will be updated. So min value is equal to 0xFFFFFFFF, which is the maximum value that you can write into 32-bit register, and max value we will set equal to 0, so that when we search for them, they get updated. So let's write a loop for I equals 0, I smaller than 10, I plus plus. If value buffer with index I is greater than max value, then we need to, if there is any sample that is greater than current max value, which is initially 0, then we need to update the max value to the value that is inside the buffer's ith element. So max value equal to value buffer element number I. And the same for minimum value. If min value is smaller, sorry, if, okay, let's write it the opposite way. If value buffer element number I is smaller than current min value value, then we need to update it. Min value is equal to value buffer element number I. So min value is initially set to a very large number, so it will be probably updated in the first iteration. Same for max value. And this way, going through every element inside of value buffer, max value at the end of this loop will have the same value as the largest value inside this buffer, or the largest sample, and min value will be equal to smallest among the value buffer values. Now, to average, to remove, so basically to calculate the average of all values, but remove max value and min value, what we can do is we can create an accumulator. So unsigned 32-bit integer accumulator equals 0. We need to sum all of these value buffer values into this accumulator. Then we subtract the maximum value, then we subtract minimum value, and then we divide by 8 so that we do this algorithm. So for I equals 0, I smaller than 10, I plus plus, accumulator plus equal to value buffer element number I. So this plus equal means add this value to this variable. Then accumulator minus equal min value, accumulator minus equal max value, and result equals to accumulator divided by 8. Oh yeah, and before we do the sampling, we need to open this excitation pin. So I put it here, and we also need to delay the excitation time, and only then we do the sampling. And so I remove these lines here, and we return result. So this is how our updated code looks like. Too many white spaces, maybe. Okay, so like this, we turn on this excitation circuit. We wait for this minimum time for the transistor to stabilize. Then we initialize the channel with acquisition time 64 and oversampling mode. So each sample is actually sum of 16 quick samples. Then we do this 10 times. So we get 10 times 16 sample sums. Then we also find the maximum and minimum value. We add all of the values together and then subtract the minimum and maximum value. We remove them this way. And then the result is the sum of all values minus minimum and maximum divided by 8. And then we disable this excitation and return result. So let's build this thing. Let's flash it to device. Now let's clear and let's see how much these values vary. Okay, so the code works. Now we should evaluate somehow whether this RC filter did any good, whether this oversampling do any good, and whether this averaging minus mean and max value do any good, and we can quantify it using Excel. So let's write the following code. So in the main loop, we will make the code in the following way. So let's do 100 samples of get light level. Let's just print them out. For I equals to 0, I smaller than 100, I plus plus, print f. And let's not write, light level equals to the number, but let's just print out that number. So we can copy it into Excel. So print %u, new line, and analog get light level. And that's all that we want. And then we let the program run. So let's build it. Let's flash it into device. Also, I cleared the screen. And here we have 100 samples. So I pause this termite so I can copy them into Excel. So this value, this variability is with maximum filtering. And to analyze this data, I paste it in Excel. And also I will insert a line, and this is oversampling plus averaging. In the next column, let's run the same code. Oh yeah, and let's also write the time for each sampling. So analog get light level. Let's make it in the following way. When we do the sampling, we turn on the LED, and when we finish, then we turn the LED off so that we understand how long time we need for each sample. So when we enter analog get light level, let's turn on LED. So LED1 underscore, sorry, LED on, LED1, or LED0, because we have two LEDs. And when we finish this whole thing before exiting, also, but before sampling, sorry, let's put it right here before we start sampling. And when we exit, LED off, LED0. Okay, so let's test this code. So we print out 100 samples, and when we start the sample, we turn on LED. And when we finish, we turn off the LED. So I build this thing. There's an error. Oh yeah, because we need to include in analog.h this leds.h header so that we can access the API. It compiled without mistakes. Now I flash to device. Okay, it's not so good. Yeah, instead of LED 1, which is LED 0, which is run by the fast timer, let's use LED 1. So LED 1 turn on, LED 1 let's turn off, and in our system we comment out let toggle so that this real-time counter doesn't tamper with our data. So we build it, flash it to a device, program, and also inside the energy profiler, let's start energy capture. And let's just see how long time it takes for one sample to be obtained. So it's right here. So when the processor wakes up, where's the main code? Right here. So when the processor wakes up, it measures the light level. And this whole process takes something like 10 milliseconds, 10.7 milliseconds. Now, and also we have obtained the sampling data right here. Next thing that I want to do is try out the sampling, but with less filtering. And let's see if the signal gets more noisy. So this is maximum filtering. And now I want this code to just do the oversampling 16 times, but no averaging. So I will take all of this code and I will comment it out. And instead of all of this, I'll do just one sample. So I will start analog to digital converter. And unsigned integer 32-bit, result equals to ADC data single get, and that's all. So it initializes the thing to oversampling, read out one value, and that's it, and just exit without calculating, averages or something. And let's build this thing. Oh yeah, and I'll write down that the time for this thing was 10.5 milliseconds. So this thing is just oversampling. Oversampling is still on, but we do one sample. So I build it, I flash it to device, and in termite I clear and connect. Let's start over. Okay, and these are all of the samples. So it's less, but I'm not sure why. Maybe I moved this development kit a little bit so it's in a little bit darker place because I'm moving it with my mouse. But what we're interested in is not really that much precision, but how much noise and variability we have here. So without averaging, let's look at energy profiler. Let's zoom in. The time for this whole while true loop is much smaller. It's now only 9 milliseconds. It was 10.5. Now it's 9. So what we can derive from this is that averaging took 1.5 milliseconds, these 10 samples and then adding them all together and so on. It took 1.5 milliseconds. So of course, averaging takes some time. This is why the code runs longer. Let's end the session. And the next thing that we want to find out, if we switch off oversampling and do just one 12-bit sample, how much will the output change then? So let's build it with 12 bits switched on. Instead of oversampling, now it will be just one 12-bit sample. Let's flash it to device and also clear and connect, and I'll restart this board. So these values is what I obtained. In this case, so it's just 12-bit values. And let's look at the time difference. So it's 8.8 milliseconds. It's actually a little bit less. Sorry, previously I measured from this point to this point. It is 8.7 milliseconds. So it's 0.3 milliseconds less, 300 microseconds less. So of course, less sampling, less time, 8.7 milliseconds. And now, finally, let's also do the test and session with RC filter off. So in analog to digital converter settings, I will now switch off this RC filter, and it will be just directly connected to the signal with no filtering and program. And I expect that, of course, we will have even greater variability in output. Okay, so let's pause this thing and put it here. The time should not change, but let's see. So actually, if we are not using the RC filter, we could have reduced the acquisition time, because this filter added quite a bit of time to acquisition. But here you can see it's 8.5 milliseconds, 8.6, that's a measurement error, 8.7. Okay, so it's 8.7 milliseconds. It's the same time. And now let's check out how much of the noise we have in each of these samples. To calculate noise, we basically can calculate standard deviation of these samples, right? So I type equal to STD deviation. There's STD standard deviation on whole population or samples. It doesn't matter here. So I'll just calculate standard deviation of this range. And it says 7.88. And we should also calculate average and relative deviation, because deviation on larger numbers will be larger than for others. For example, here we have smaller numbers, so the deviation is also smaller. So we will also calculate average. Of these numbers. And then relative average. I don't know, it says 44 here. That's a big deviation. I don't know, maybe the development kit was moving during that time or something like that. I don't know why it's so big. But let's calculate relative deviation equals to standard deviation divided by average, so that we normalize it relative to the magnitude of this number. And it's a small number, so let's multiply it by 1000. So equal to this number times 1000. And as we can see, actually averaging out 10 samples and removing top and bottom value reduced our relative variability greatly. What we can see here is, so this column is with no filtering at all, and its relative deviation is very similar to having this RC filter on. So that RC filter is pretty small, and maybe the signal is very silent, so there's not much difference here. And when we turned on oversampling with filter, oversampling didn't really change much at the noise level, probably because it's been sampled very quickly and these values don't really differ that much. But if we did 10 separate samples and we removed top and bottom values, then we can see that the noise magnitude is reduced significantly. So sampling, removing top and bottom, and then calculating the average removed noise the best. And, this is how we can uh, measure it by sampling, outputting in termite, and then copying to Excel, and then looking at these numbers and calculating standard deviation, average, and then relative deviation to the average. And here we can see that oversampling plus averaging plus RC filter gave the best results. But RC filter didn't change much the signal, but it would change the signal much if the signal was more noisy. If you're sampling something over long lines, for example, you have to use some capacitor for decoupling. Okay, so that's all for this lab. We measured the variability and different sampling techniques. So I will now revert this analog.c file to this best filtering level with oversampling and averaging. To do that, again, in analog to digital converters settings, we change its oversampling rate select to 16. Then we also, let's just enable this low pass RC filter. Then in this analog get light level, we change the resolution to oversampling. Acquisition time we had to increase. Let's remove this LED control. We remove this as well. And let's leave this part on because it gave the best filtering. This oversampling and RC filter, they didn't do much. But this part gave the best results. So let's check out if I have modified something else. So in analog.c, this is the analog init function. We changed it a little bit. Then analog get light level, we updated it in such a way that it samples 10 samples, removes the max value and min value, and then divides the remainder with 8. And that's our result. And we reduced the variability of the signal significantly. And get core temperature, we didn't change. Let's see, connect. And in main code, we wrote this thing that quickly samples 100 samples and outputs them. So we can copy them into Excel and check out their value. So I can leave this code here, but generally nothing much changed. So your job, and also, yeah, the rest is the same. Now your job is to type down this code into your Simplicity Studio, compile it, upload it, and check out that it works, and also check out how the noise became smaller. So on this development kit, if I put this sensor in darkness, it shows less. If I put it in light, it shows more. So analog signals are not so easy to manage. As soon as you add some filtering, you add extra time for the filter to charge up or down the capacitor. And then you also need to do some averaging to remove noise. So it's actually some testing is necessary always to do analog signal processing on this microcontroller. Okay, so that's all for this lab. Write the code, compile, test it, check out that it also outputs the same that it outputs on my CPU, on my microcontroller, and then upload it on Artus.